in order for something to be a basis, we need to have a linearly independent set that also spans the space. So those two properties and two things we know what those definitions mean, right? Linearly independent set means that they're not linear combinations of each other. And then spanning the space means that anything in the space can be used to construct, any element in the space is some linear combination of those vectors. And so I think a really nice example of that in the real world is that what I have right here. The periodic table is a basis for the natural world, right? So the elements on the periodic table themselves are as simple as they can get, right? As reduced as they can get. You can't take hydrogen and oxygen and make anything else but hydrogen and oxygen, right? But when you take linear combinations of them, like hydrogen, two hydrogens plus one oxygen, then you get water, for example, right? And so the elements themselves are linearly independent, but anything in the natural world can be constructed using linear combinations of them. So if you can keep that in mind for the periodic table, I think that's usually helpful for conceptual understanding of it. But in terms of practically doing these problems, something's a basis if, like we said, linear independent and spanning the space. And so if we've got a bunch of vectors, these four, for example, and we want to know if they're linearly independent or if they span a space, you put them in a matrix and you row reduce. And when we row reduce, it actually stays the same in this case. And in this case, we see there's no free variables, which would mean that's linearly independent. And we see there's a pivot in every row, which means it spans a space. And so this is evidence that these four vectors form a basis for R4, just for example. Okay, I'm going to get to the specific question that I had about this set, but are there questions about anything I just said? Anything that people would like me to clarify about what I just said there? So the question then that I got was this one, 4.3, number 8, and it gives you a matrix and it says, find a basis for the column space. And so on the very last page of 4.3, it talks about how to do that. It says the pivot columns of a matrix are that form a basis for the column space. And so in this specific example, here is the matrix we were given, In order to find the pivot columns, you row reduce, right? And so when you row reduce, you see that these are the pivot columns. But then you go back to the original matrix and pick those columns. So like reducing, it tells you which columns to pick, but then you pick them from the original, right? And so the basis for this column space were those two columns, because those are the pivot columns, which turned out to be those two, right? So on this particular problem then, you would row reduce. You would find the pivot columns. And then you choose the pivot columns, but from the original matrix. That's the thing that maybe people are not remembering, right? You reduce it to figure out where the pivots are, but then you go back to the original and choose those. So you can see it's telling you there's going to be two, right? And so one of these columns is a linear combination of the other two is the idea. And so you don't need that one. And so you get rid of it after you row reduce and figure out which one you don't need. Okay, questions about that one or other things from 4.3? I didn't actually finish this one, obviously. You would have to row reduce it, but it's not a hard problem once you see the process. Any thoughts about that one?
Could you do problem 11 from 4.3? I did it, but I'm not sure if I went about it the right way.
Sure, let me open that one up quick. Yeah, so I'm trying to remember if I did an example kind of like this one. So it's and this is sort of kind of like the next one I had a question for too, actually. So 4.3, let me put down the question that was asked. And give me 1 second. So the question, this is number 11. Yours might look a little bit different. Sometimes these are generated differently, but it says, so it gives you 3 vectors in a polynomial space. Most of the time we work in Rn in this course, but I do try to introduce polynomial spaces and sometimes some matrix spaces just to keep in mind that vector spaces and these properties of bases, these concepts of bases and things like that extend beyond just Rn, right? Because we learned about how, yes, Rn is a vector space, but there's lots of other vector spaces. And so this particular space is any polynomial that can be written as a linear combination of those 3 things, right? That's what it means to be spanned by those things. And so part A says, is this the same vector? Yeah. Is this a basis for P2? And so this is polynomials of degree at most 2. And so P2 would be ax squared plus bx plus c, where a, b, and c are any real numbers. So I think it was William who asked that question. I can't remember. Maybe it was CJ. I can't remember. I'm not really, not CJ. DJ. But whoever asked that question, what were your thoughts about this one? Or anyone? Like, what's a good approach here? So if it's a basis, they need to be linearly independent, and they need to span the space. Thoughts?
So like I just put them all into a matrix and then checked to see if it was if there was a pivot in every row, like to see if it spanned the space. But I don't think that's the right way to do it.
Yeah. So I would say, let's see here. I'm trying to find something in the notes that would help us. Maybe it's not in this section. Maybe this was a little preemptive to put it in here. I really liked this one. Yeah, this is really a question for 4.4 probably, because it's more like page 15 on 4.4. But both of those are technically due Wednesday, so we could look at both of them. Like 4.4 is the one that's supposed to be due for today. So this is 4.4. This is page 15 and 4.4. And in this example, we showed that this set was linearly independent. And so we can use the concept from here to determine if they're linearly independent, which maybe it sounds like that's what you did. Maybe this is what your matrix looks like. You put like the coefficients in there basically, right?
Yeah, pretty much. But like I tried it like both ways. Like I tried it like horizontal and then vertical. But like I noticed when I did it I think vertically, like in this example, like when I put everything in, I had a pivot in each row, but the answer was that it was not a basis for P2. So I don't know what went wrong. But then when I did it like when I put them in like horizontally, I didn't have a pivot in every row.
So right. So notice the way that it was entered like this. So like 1 minus t squared. We use the basis. It sounds like maybe you were doing t squared t1 the first time. So in other words, like this first row is the coordinates for this first. This isn't right either. What's going on here? V1. Oh, yeah. Right now, you're right. This is confusing. So this is when you put it into this matrix. This is the like V1 row, V2, V3. So 1, 0, minus 1 is this first vector. So it is, you put them in as rows. So like on this one, for example, we would enter this one as this first one. We're going to use the basis 1, t squared. And so when we enter this first row, it's like minus 1, 2, 1. I mean column. That would be this first v1. That's v1, v2, v3. The second one would be minus 1, 0, 2. This should be x, sorry. And then this one would be 3. Did I enter that one right? Yeah, 3, 2, minus 7. And then you would row reduce. So basically, you're like writing this set as a basis that we know exists. This is, again, following page 15. And then if it has a pivot in each row, we would say it's linearly independent. But what you're going to see when you row reduce this one, I don't know what it ends up being, but you're going to have a free variable, which means they're not linearly independent. And whichever one, and so part B, the question for B then is, so if they're not linearly independent, then it's not a basis, because you need it to be linear independent. So that's why the first answer is no. But then part B says, what is a basis then? See, when you do this and you realize that when you do this problem, when you see that there's a free variable, that means that one of these three vectors is a linear combination of the other two. Let me say that again. When you get a free variable, that means that one of these three vectors, right, one of these three polynomials is a linear combination of the other two. And so that means you don't really need that one to be in the basis, because you can just construct it using the other two, right? And so when you figure out where the free variable is, you would remove that corresponding entry from the basis. This is very similar to the one we just did, right? You find where the pivots are, and then you choose the pivots from the original. So you would do the same thing here. You would choose the polynomials that correspond to the pivot columns. I apologize. This one should have probably been in 4.4, but we're talking about 4.3 and 4.4 today, so it's not that off. But it probably should be the next one. So yeah, is that the last question? This is the last question, right? So it's definitely a harder question. I'm trying to extend things a little bit and challenge you. I didn't mean to make it confusing and out of section, though. I apologize for that. But can I clarify something about what I've said there? Are there other thoughts?
How did you come up with the coefficients again? I'm a little bit hazy on that.
Yeah. So basically the idea is this kind of gets into section 4.4. So let me say something about 4.4 and then we come back to exactly what you said. So in 4.4, what we're doing now is we're taking bases and we're writing vectors in terms of their basis coordinates. So for example, in this first problem, we're being told that these two vectors, b1 and b2, form a basis for R2, and we want to find the coordinate vector for x. And so that means there's some linear combination of b1 and b2 that equals x. And so that's what we do. We set it up like b1 plus b2 equals x. Some linear combination equals that. That's just a linear system. You put it in a matrix and you solve the matrix, right? And so in other words, minus 6 times this one plus 2 times this one equals 4, 0. And so we say those weights end up being the coordinate vector. Now, this applies to that last problem because what you see on the next page is, well, let me just, so on this one then, this matrix that we set up, is this blurry? It's a little bit blurry on my screen. Let me try to focus here. So this matrix that we set up here, this is let me get my notation right. This is the coordinate vector for V1. This is the coordinate vector for V2 based on that basis, where this is the basis. Right, we're using this basis. And this is the coordinate vector for V3. So it's like, how can I construct this first vector, x squared plus 2x plus 1? Oops, I'm sorry, I'm off the screen. How can I construct this first vector using these three things? Right, well, it's -1 of these, plus 2 of these, plus 1 of these. And so that's how this first column ended up being -1, 2, 1. Because I'm doing the coordinate vectors of this with respect to that basis.
Could you technically also do it backwards, wherein the very first one is the squared, the next one is just the x, and the next one is the 1?
Sure, yeah, you could do that. So that would just be a matter of changing the rows, and we know that you can change rows and keep things the same. Yep.
Okay.
We usually, just the way that the bases are usually written in the textbook and things, it starts with the smallest power, at least from what I've seen. So that's why I just tried to be consistent with that. But yeah, you're absolutely right. We could just reorder the rows here, and we know that that doesn't change anything. And so you could go the other way, yeah. But what you can't do is put them on the rows, right? So that's what I'm sorry, I wasn't sure who asked that first question, but that's what whoever was asked the question to begin with was. They had maybe tried to put them in the rows first, and then when you row reduce that, you're going to get something different than if you put them in the columns.
Yeah, I tried that after putting it in the columns because that didn't work, but then I realized the only reason why putting it into the columns didn't work is because I forgot to make something negative. So.
Oh, okay, cool. So did it row reduce to the same thing?
Well, yeah, now it row reduced, and when I put them in the columns, it row reduced, and I didn't have a pivot in every row, so that makes sense why it didn't span, why it wasn't a basis for P2.
Gotcha. Good. Glad to hear it. So this was number 11. Oh, so then the other question I had for 4.4 is also similar to this, all this stuff we're talking about. So let's just look at that real quick. It's also another polynomial one, problem number 3, that looks like this, where we're being told that this set is a basis. So this is 1, 2, 3 elements, and it is a basis for P2. And so we know that those things are linearly independent, and we know that they span the space. And so this is a vector in P2, right? This is a specific polynomial in P2, and we want to find the coordinates that you can multiply these vectors by in the basis to get that polynomial. So the question is, what times the first one plus what times the second one plus what times the third one equals the vector we're trying to figure out. And I did one very similar to this at the top of page 15 too, right? This is almost the same problem. I'm saying here's a basis, find the coordinate vector for this specific polynomial. So it's very similar to that problem, just with a different basis. So maybe let me just run through that problem instead of, I'd like you to actually try this one. So let's just look at the one from the notes. So we did the same thing, right? So here are 3 basis elements. So you do C1 times the first one, C2 times the second one, C3 times the third one, and we want it to equal the given polynomial, right? And so you distribute the C1, C2, C3, and then you rearrange things and group the t's, the t squareds, and the constants together, right? So when I group all the constants, you'd get C1 from this one, you'd get nothing from this one, but then you'd get 2C3 from this one. So the constant was just this, right? That's the constant terms. If I grouped the t squareds together, there'd be a minus C1 from this one. That's where this came from. There'd be a minus C2 from this one. And then there'd be a plus C3 from this one. Right? So you just like group the things together. And now you want, again, right, you want this thing on the left to equal that polynomial. And so that means the coefficients in front of the t squareds on the left needs to be -6. And the coefficients in front of the t needs to be 1. And the coefficients that are constants needs to equal 3. And so it sets up a linear system that you can solve, right? Once you write it like this, oh, hey, we can put that in a matrix and solve it. And so this is just translates to a normal matrix. We row reduce like we always do. There will be a pivot in every row. We know there's going to be a pivot in every row because we know these things are linearly independent because we know it's a basis. And so it's gonna row reduce to the identity matrix, and then whatever the column is on the right are the coefficients that you would use. And so that is going to be the answer. And so that's what you do on this one. Sorry, I didn't just sort of do that to begin with, but you'd rearrange, you distribute the CIs, group in this case we have X's, so group the constants, CIs, the X CIs, and the X squared CIs, and create linear system to solve. You can really follow the exact steps on page 15 for this one. So I don't know, whoever asked that one, if that's helpful, if you had something else in mind. Maybe you didn't see that page in the notes, or maybe you tried it and didn't get that. I don't know, but can I clarify something? This helped. Great. Yeah, so these two sections are, I don't know how to describe them. They're different. I think they're pretty important. Like, this is the kind of stuff that comes up in future courses. Like, bases are absolutely a big takeaway from linear algebra. And I know we're dealing in these polynomial spaces, which can be a little bit tricky and unfamiliar. So it's definitely understandable that there'd be questions about this stuff, especially these ones that we've been looking at. But I'm also I'm more than happy to just go over the notes. Like, if you're sitting there and you're like, man, I don't even understand what we're talking about because I didn't really get page whatever in the notes. That's what these sessions are for. Please don't feel, I get emails sometimes that are like, oh, I had this question, but I didn't want to ask it during the session because I was embarrassed, or I didn't think, I thought everyone knew. Like, the point of these sessions are so you can ask questions like that. Like, can you go back over page 4? Can you re-explain whatever from the notes so that the homework makes more sense? So anyway, let's try and encourage you to, if you do have some questions about the notes, now's a good time. .3 and number 4. Let me take a quick peek at that one. Yeah. So back to 4.3, number 4. It says find basis for this subspace. So this is in R3 because it's like, if we're in R3, we know that X's look like X1, X2, X3, right? They have 3 entries. And so this space is saying it's including every vector in R3 such that when you multiply -9 times the first entry, -3 times the second entry, plus 4 times the third entry, you get 0, right? And so we're in R3, but it's a very specific subspace of R3. It's like a line going through R3. And the hint here says, consider this a system of one homogeneous equation and solve. So let me try to relate it to something in the notes again. I mean, basically, we just want to solve this system, but I'm trying to maybe point out to what it would look similar in the notes. We didn't really do one very similar to this one, so I guess we could do this one together. I actually had one in the homework, in the written homework, that was just like this one, which is why I like to pick this one out. So anyway, we can think about this like the hint says. It says, hint, consider this a system of one homogeneous equation, right? So this is an equation, and so we can solve the system. And you really don't even need to row reduce it because, I mean, I guess we can. Let's just go ahead and row reduce it. So -9, -3, 4, 0. If we do RREF, right, it's just going to put a pivot right there, which means dividing everything by -9. And so this is going to be 1, 1/3, -4/9, 0. And so we see that x2 and x3 are free. And so when we solve the system, we would say x1 equals -1/3 x2 plus 4/9 x3. And if we wrote that out, x2 is free and x3 is free, right? x2 equals x2, x3 equals x3. And so this parametric version of this solution would be -1/3 10 x2 plus 4/9 0 x3. In other words, we're trying to characterize what vectors in this space look like. And so we're solving this system, which is, you could also think of as just like adding things to the other side and dividing by 9, right? If it's just an equation, you would get to this answer just by getting x1 by itself. Right? In other words, if you solve for x1, you would just get this equation. And that's the answer, right? So this tells you how to write x1 in terms of the other two. We know the other two are going to be free. And that's it. And so the answer in this one, it wants you to enter two vectors, and it would be this vector and this vector. Although yours might be a little different. Keep in mind that depending on the question, most of them are the numbers are randomly generated. So you may have different numbers that you need to solve separately. What else can I help with? Are there any other test questions? Questions from test one that people would like to go over now that they've had a chance to look at solutions and things like that? Problem 9, sure, hold on a second. So number 9 is asking for a basis for the null space. And I just want to point out to you where we did this in the notes. So technically that's from 4.3. So I guess you kind of have to combine stuff from 4.3 and 4.4 to think about this basis of a null space. Thought we did one of these, but maybe I'm mistaken. Okay, so basis for a null space. So this is 4.3, number 9. Again, I'm probably not going to solve this one, just sort of set it up for you. So x, a vector x, is in the null space of the matrix A if A times x equals 0. And so if you're given a matrix A and you want to find the basis for the null space, you solve the homogeneous equation. So in this particular problem, we're given this matrix. And heck, row 1 is -1 times row 2. And so we could pretty much just do this one without thinking too hard. So we want to solve ax equals 0 for null space. And since this one's so easy, we can just see that we can see how to do this, right? I'm just going to do it by hand just for fun because it looks like a fun one. So we set it equal to 0, and we want to solve it. Let's add the rows together. Let's do row 2 plus row 1. And that's going to pretty much do it. And so x2, x3, x4 are free. I guess we could divide row 1 by 9 if we really wanted to get it fully in reduced form. Be 1, 1/3, 1/3, minus 2/3. And again, free, free, free. So solve this, and that'll be your answer. Your answer will look something like, something times x2, something times x3, something times x4. And those three somethings are what you would add, enter, I mean. Very similar to the one we just looked at a second ago. It's actually the same problem as the one we just looked at a second ago. This was a homogeneous system as well. It was just one equation, except the question for this one was, it's not asking like the basis for the null space. We just realized, hey, this is a null space because it's equal to 0. It's actually a very similar problem, just kind of phrased a little bit differently. Anything else today? I love working these problems. I'd be happy to do some more.
Maybe 4.4, number 6. Like, I know how to do it, but just the way that I did it was kind of I'm not sure if it was optimal.
Sure, let me pull that one open. Just kind of checked. Looks like the people who are asking questions are the only ones who have started this homework. So I appreciate you guys for starting and asking these questions, and I hope everyone else in the class appreciates you because they're going to have some answers. So yeah, let's look at. So this is the last problem in number 4.4. Number 6. Oh, it's a matrix problem. Cool. So our basis set, or our basis for upper triangular matrices is this. So that's a basis for upper triangular matrix. Remember, upper triangular means that everything below the diagonal is 0. So you can see in a 2 by 2, below the diagonal is just the lower left-hand corner. And so we see that they're all 0. And so it turns out basically any 2 by 2 matrix, any upper triangular 2 by 2 is going to look like this. There's going to be a 0 right there. And so anything that looks like that is some linear combination of those three. That's what this is telling us. And so it wants us to find the coordinates for this matrix. So this is similar to like number 3 that we did, where we're going to like do a linear combination of the basis elements and set it equal to the thing we want. And then that's going to we'll be able to create a linear system from that, and we'll be able to row reduce and solve. So in this particular one, we want to add these threes together and get this one here. And so it's C1 times this one, C2 times this one, C3 times this one. And we want that to be this. Is this how you approach this one?
Yeah, that's exactly what I did.
So that's what you're going to want to do. So let me just do one more step here. This would be
That's
like
how I approached it too. However, I feel like the way that and assuming that William, I feel like William also might have done it like in the same way that I did. I feel like there's probably is there a more like systematic way of doing this? Because I feel like this one it was kind of easy to intuit because it's -9, -1, and then a 0, right? So the first thing that I did was I said, okay, what will make that like top left one 9? Because that one has a 0 place and all of the ones that come after it, right?
it sounds like maybe you have a different matrix though, right?
Actually, I have. Oh, mine is slightly different, but anyway, mine was slightly different, but like the whole rule with the 0 is still applied.
Yeah,
Like,
I mean, I agree that this one is pretty. You might not need to do a system thing. You might just be able to intuitively figure it out. Like for example, the only thing in the upper left-hand corner is this one, right? This has a 0, that has a 0, and so you're going to have minus C1 here in the upper left-hand corner, and you want that to end up being a 0. And so right off the bat, C1 has to be 0. Is that the kind of thing you're sort of thinking about?
Yeah. Oh,
So
yeah.
you may not need to actually do a linear system if it's simple enough to just kind of see. But you could still do the linear system. You'd still get the same answer. Right, like on the next one, we'd have minus 3C1 plus or minus C2, and then they get a 0. So then we want, and that's supposed to be minus 5. And so we would also have minus 3C1 minus C2 equals -5. Now, if we didn't know C1, we might need a linear system. But if we know C1 0, then all of a sudden this one goes away, and we know that C2 equals 5. Right, and then we just would find C3. So we're going to get a 0 in that corner because they're all zeros. And then we'll get 3C2 minus 2C3. And so then we want that to be -2. We know that C2 is 5. And so this is 15. And so we would subtract that. We'd get -17. So I think C3 equals 17 halves. Is that right? So it feels like it should be a whole number if the other two are. Let me double check the answers. Yeah, that's right.
So could you do it as like a linear system? Like say like you multiply all the scalars throughout each of the matrices, and then you just get like one matrix, but then you have to set that equal to another matrix. Like how would you go about doing that as like just could you just put everything into a matrix and then solve it, or would that not work?
No, yeah, so the linear system here, this is the way it's set up, right? And so we have minus C1 should be 0. So this is one of the equations in the system. This should be -5. So this is one of the other equations in the system. And this should be -2. And so this would be the third equation in the system. So you would set that up like, we got a little bit of room here. You want it to equal, let's see, 1, 0, 0, 0, minus 3, minus 1, 0, minus 5, 0, 3, minus 2, minus 2. So that would be the system that would be what the system looks like if you wanted to set up like a matrix. And then if you did RREF, you would get the solution. So you'd get 1, 0, 0, 0, 1, 0, 0, 0, 1, and then you'd get 0, 5, 17 halves.
Okay, yeah, I got it now.
I'm still a bit puzzled. How did you get those coefficients again? Like, how did you put the matrices, the matrices in the matrix like that?
So it's a little bit confusing written like that. Let me rewrite the system. The system is C1 equals 0, minus 3C1 minus C2 equals -5, and then 3C2 minus 2C3 equals -2. So I'm just taking the coefficients, right? So then the first equation, it's there's only a 1 in front of the C1, nothing else. So that's why it's 1, 0, 0, 0. I've got minus 3c1, minus 1c2, no c3, and a minus 5. So minus 3, minus 1, no c3, negative 5. Right, there's no c1 in this equation, so that's why I've got a 0 right here. And so this will always work, just to be clear. It just turned out that this first equation told you one of the values. And so you can just use that to get this one, right? And then once you know that one, you could use that to get the third one. And so you don't need to do row reduction on this one just because the way that this particular one was generated, you didn't necessarily need to. But if yours is generated differently,
failing to see how like the first matrix in the B corresponds to like the 1 and the second one corresponds to the...
So this is the C1 column, C2 column, C3 column, constant column with B, I guess. All right, so the C1 coefficients are 1, negative 3, 0. The C2 coefficients are 0, negative 1, 3.
Like, for instance, why is the negative 3? Oh, wait, actually, hold on, wait a minute.
The negative 3 is with the C1, which means it goes in the C1 column. Right, would it be helpful to write it like this? C1 plus 0, C2 plus 0, C3 equals 0. Minus 3C1 minus 1C2 plus 0C3 equals negative 5. 0C1 plus 3C2 minus 2C3 equals 2. Right, now the coefficients here line directly to that.
So is the fact that that is like a triangular matrix allowing us to like ignore certain values when we like put it into the matrix that we use to solve it?
Yeah, so that's a good point, right? These things have 4 entries in them, but because they're upward triangular, the lower left one is 0. And so we only get 3 equations out of this because the fourth equation is 0 plus 0 equals 0.
Oh, okay.
We don't have any coefficients for that one.
Okay. Yeah, the part that I was confused on is actually getting like the augmented matrix from that. But now I understand.
And so the fact, if this was not a triangular matrix, we would need another element in the basis. The fact that there's only 3 elements for 4 entries is because one of them is 0. Right? If it was a non-zero in the lower left hand, we'd need another thing in the basis.
So in general, when we get a question like this, sort of the algorithm for doing it is we just for each row put it into a column in the augmented matrix, just reading it from like left to right.
I mean,
so like,
yeah, go ahead.
So if we did have to put, if it wasn't triangular and we had to put all 4 of them in, then would say the first column be -1, -3, 0, 0.
Yes.
Okay. So and then we would just solve the augmented matrix as as you usually would. So
right.
Okay, I think I understand this now. I was just a little confused on how to get the augmented matrix from the original ones.
Sure. So maybe let me just write that like the general process, because you're right. To me, these are all very similar problems because we're doing the same thing, right? We're trying to find this in all of them. But sometimes X is in Rn, sometimes it's in P2, sometimes it's a matrix. And so the general process is 1, write linear combination of basis elements that are in beta and set it equal to X, whatever X is. If it's an Rn, then it's a vector. If it's a polynomial space, it's a polynomial. All right, so let me be clear about that. X could be in Rn, it could be in Pn, in some cases it could be in the matrix space. All right, those are the different ones we've seen. Once you do that, you should be able to create a linear system where the coefficients of the linear combination equal the coefficients or the values, depending on what it is, in X. And then you solve the linear system in a matrix. That's sort of the general process. I will scan that page in with the stuff today if you want to sort of have that to help you as you go. And if you haven't looked at this section yet, which is about half the class from what I can see, you're probably really lost, but I hope you'll remember to come back to this video when you're looking at these problems and after you watch the actual course notes and see if this helps you. What else? Okay, well, if there's anything else, thank you all for those folks who are really keeping up with things and driving these questions. I hope this has been helpful, and I know it will be helpful for everyone after they do watch the video and are ready to do this homework. So I'm around if you need some more help.